Hi there! I hope that you're all doing very well and are ready for today's class. I know I am. I am your personal math and physics tutor, Dr. Rima McMullen. And I'm on a mission to bring education to everybody sitting at their home, to make everybody believe that they can too do math and physics, that we are all made to do it, as long as we put our mind, our heart, our effort, our 100% into it. When we do that, there's no reason why we can't do something. And I'm a live example of that. With that being said, let's talk about today's class. This class is lecture number 9 on problems of propagation of error as applied to simple pendulum. What's a simple pendulum? You can think of a simple pendulum as an object with some mass that is attached to a string, and that string is suspended from some support point. So something like this. Think of this yellow pencil as a string and imagine that my hand that's holding it is kind of a mass. And this string, it is suspended from some support point, like my top hand over here. And this pendulum, this mass can oscillate back and forth. So something like this. And this string, it has some special properties. This string is going to be inextensible. That means it's not stretchy. As well as this string is massless. So what we're going to do is we're going to apply the rules of propagation of error to problems based on simple pendulum. Let's look at our first problem. Here's our problem number 1. It says that the time period t, uppercase T, of a simple pendulum is given by the following equation. Here's our equation. T equals 2 pi times square root of L over G. Here, this length L is the length of the pendulum, and it is measured to be 100 centimeters using a meter stick with a resolution of 0.1 millimeters. Okay, the period is measured to be 2.0 seconds using a stopwatch with a resolution of 1 milliseconds. The percentage error and the error in the determination of G, the acceleration due to gravity, are found to be. So we have these 4 answer choices. We're going to solve the problem to figure out which of these 4 answer choices is the correct one. So let's go ahead and begin with writing down what is given to us. Make a list of what is given and write down what you want to solve for, and then try to connect from what you have, what you're given, to where you want to go, what you want to solve for. What connects the two? Let's see how to do that. We know that the length L of the pendulum is 100 centimeters. And the resolution is 0.1 millimeter. Now the resolution, let me write it over here, can also be called as the least count, which can be considered as the uncertainty or the error in the measurement. So that means delta L equals 0.1 millimeters. Now how do we typically write length? We write it as L plus minus delta L. And we have said this before, that the delta L must have as many digits after the decimal as the actual measurement does. So since the delta L is 0.1 millimeter, what we're going to do is we're going to convert this 100 centimeters into millimeters and also to 1 digit after the decimal place. So that means this L is going to become 1000.0 millimeters. Now it matches the number of digits after the decimal for delta L. Likewise, the time period is given to be what? time period is 2.0 seconds, and the resolution in the time period or the time is 1 milliseconds. Okay? So uppercase T is given to be 2.0 seconds, while delta T is given to be 1 milliseconds. So what we will do is we'll write this 2.0 seconds in the same units as delta T, and to the same number of digits after the decimal as delta T does. Now delta T is an integer. That means T will become just 2000 milliseconds. So here's what we have now. We have L plus minus delta L is 1000.0 plus minus 0.1 millimeters. And we have T plus minus delta T, this is the time period, equal to 2000 plus minus 1 milliseconds. Okay, and we are asked to determine the percentage error and error in the determination of G. So solve for, find out what? Percentage error in G, the acceleration due to gravity, is delta G over G times 100. That's the first thing you're asked to solve for, but that's not it. We're also asked to solve for delta G, which is the error in the determination of G. Okay, what else are we given? We are given time period T equals 2 pi square root of L over G under the square root. Okay, so from this equation, we are to calculate this G. We know T, we know L. And 2 pi, that's just a constant number. So can you solve for G from this equation? Yes, we can. How? First, take square of both sides. When you take the square of both sides, why are we taking square of both sides? To get this G out of the square root symbol. Next thing we're going to do is to multiply G on both sides of the equation. And we are going to divide both sides of the equation by T squared as well. So what does that give us? That gives us G equals 4 pi squared times L divided by T squared. Next, we are going to apply the rules of propagation of error to this equation for G. And when we do so, what we get is that the relative error in G, which is delta G divided by G equals, now this 4 pi squared, it's a constant. Constant has no uncertainty, therefore no error. So when we are writing down the formula for the relative error in G using this equation, we're going to disregard this constant 4 pi squared. Okay, after we have disregarded this 4 pi squared, we're going to move on to this L. We're going to write down the relative error in L plus relative error in T squared. What does that give us? 2 times relative error in T. Now, do we know delta L? Sure we do. We wrote it down here, 0.1 millimeter. L is 1000.0 millimeter. Okay, so 0.1 millimeter divided by 1000.0 millimeter plus 2 times delta T is 1 milliseconds and T is 2000 milliseconds. So that is 1 millisecond divided by 2000 milliseconds. So here now what we can do is millimeter cancels out millimeter in the first term, and milliseconds cancels out milliseconds. Next, we can get rid of this decimal by multiplying divide both sides of the first term by 10. And when we do so, what do we get? We get 1 divided by 10,000 plus the second term becomes 1 divided by 1000. And what is this equal to? This is equal to delta G over G on the left-hand side. What are we interested in though? We're interested in the percentage error in G. That means multiply both sides of the equation by 100. And when we do so, what do we get? 100 divided by 10,000 plus 100 divided by 1000. Okay, now these two zeros in the 100 cancels out two zeros at the bottom in the first term, and the two zeros in the 100 in the second term cancels out two zeros at the bottom in the second term. What does this leave us with? This leaves us with 1 over 100 plus 1 over 10. What is this equal to? 1 over 100 is equal to 0.01 and 1 over 10 is 0.1. This becomes equal to 0.11%. So the percentage error in the acceleration due to gravity is equal to 0.11%. Now, since this is a multiple choice question, let's go back to our answer choices and see if any of these answer choices is equal to 0.11%. And you see that B as well as C, they both have percentage error in acceleration due to gravity equal to 0.11%. So that rules out A and D. Next thing we need to see is, out of B and C, which one is correct? Okay. Now, to solve for part B, let me write it over here. We have solved for delta G over G times 100 to be 0.11. From here, we are asked to solve for delta G now. Okay? And when we solve for delta G using this equation, what do we get? 0.11 times G divided by 100, correct? Now we have to pick what value of G to put here. The value of acceleration due to gravity near the surface of Earth is what? 9.81 meters per second square. However, we could always round it off to 10 meters per second square. Granted, this will be an approximation. Now, can we use an approximation here? We can if these two answer choices, let me underline this with blue, if these are widely separated, then we could approximate G. But if I had one as 10.79 and the other as 10.75, then I would use the exact precise value of G, which is 9.81. In this case, I'm going to make an approximation. I'm going to say I will take G to be 10 meters per second squared. And when I do so, what do I get my answer to be? As you can see, it is 0.011 meters per second squared. And that is our answer choice number, not number, letter C. So you saw that it's not a very long problem. If you know what you're doing, you could do it very easily, very quickly. However, I want to show it to you explicitly step by step to benefit the students who might be going over these things for the first time. But if you are reviewing this, you have seen these things before, you're welcome to speed up the lecture and go at whatever pace you want to go at. And besides, like I said, I'm going to post the list of all the problems along with the answers. So feel free to check the answers. Actually, as a matter of fact, I highly recommend that you solve these problems on your own first and then check your answer. But let's say you're looking at these problems for the first time in your life. You have never seen them before. In that case, it's all right to look at one example. But when I solve the second problem, pause the video after you have seen the problem statement. Work out the problem on your own. Check your answer. Okay? Like I always say, physics and mathematics and science in general is not a spectator sport. You have to get your hands dirty. You have to put your hands in the game. Pick up paper, pick up pen, write things down, solve problems on your own. Only then they will make sense. Only then they will go in here. Otherwise, when you see other people solving them, everything looks easy. I mean, you could see somebody writing out the equations for rocket science, literally, and even they might make sense. But when you go to do the same thing on your own, things are not quite as easy as they seem to be when other people are doing it. Okay, that was that. I hope that this problem made sense to you. If you have any questions, if there is something that you didn't quite understand, I recommend that you watch this again. Okay? If you still do not understand, if you still have questions, feel free to drop those questions in the comment section and I'll do my best to get back to you with all the answers related to, again, related to what we're doing over here. All right, let's move on to problem number 2 next. Problem number 2. It is somewhat similar to problem number 1 and somewhat different. Let's see what it says. It says, in an experiment using a simple pendulum to determine the value of the acceleration due to gravity g, the total mean time taken to make 30 oscillations is measured to be 60 seconds by using a stopwatch with the least count of 1 second. Let's write this down. So what we are given is that how many oscillations are there? 30. 30 OSC. Okay, I'll write it all out. I was going to write only OSC for oscillations. How long does it take to make 30 oscillations? Time is 60 seconds. Using a stopwatch with the least count of 1 second. So delta T is 1 second. Okay. The length of the pendulum, alright, is measured to be 100 millimeters using a meter stick of least count 1 millimeter. That means L is equal to 100 millimeters and delta L is 1 millimeter. Which of the following statements is or are true? Okay, so the answer choices, they deal with the percentage error in the determination of G, A and B both, and C and D, they both deal with the error in the determination of G. So the first kind of thing we have to solve for is the percentage error in the determination of G. And the second thing we have to solve for is the error in the G. So these two things that we're asked to solve for, these are exactly the same things that we solved for in the previous problem. However, in the previous problem, we were given what? Delta T uppercase and T. But in this case, what we're given is this T, the time, complete time for 30 oscillations. This delta T over here, this is the uncertainty in the time for the stopwatch that is used to measure the time taken to make 30 oscillations. However, can we figure out uppercase T, the time period from what is given to us? Why do we need time period? Because we're asked to find the percentage error in the determination of G. And in the previous problem, problem number 1, we saw that G is equal to what? G is equal to 4 pi squared times L divided by T squared. Where did this come from? This came from this equation for time period of the simple pendulum. Just by taking the square of the second equation and rearranging it, you get this first equation. Then using the first equation, this one over here, we can figure out the percentage error in the acceleration due to gravity. But since this equation for g, it involves uppercase T, we have to solve for uppercase T. Using this information, can we solve for uppercase T? Yes, we can. Let's see how. So solution. Uppercase T is the time period to make one oscillation. So that should be equal to time taken to make n number of oscillations divided by n. In this case, to make 30 oscillations, OSC dot is oscillations, time taken is 60 seconds. So that means time taken for one oscillation is 2 seconds, not 2 oscillations. 2 seconds over here. So that's our time period. But not just that, we also need to figure out delta uppercase T. How would we do that? To do that, start out with the same equation, which is uppercase T equals lowercase t divided by n. And what we're going to do is we're going to differentiate it with respect to WRT is with respect to what? Lowercase t. That gives us d upper t divided by d lower t equals 1 over n. Because n is a constant, it comes out of the differential operator. And on the right hand side, dt over dt is just 1. We get 1 over n. Now here what I'm going to do is I'm going to go from the differential operator to the delta. You might remember that the differential is a limit of delta as delta approaches 0. So here I'm going to go in the reverse order. I'm going to go from the differential to the delta. As I have done a few times before, you must have seen it if you have watched the previous lectures. So that becomes delta t uppercase T divided by delta lowercase t equals 1 over n. And from here, if you multiply both sides of this equation with delta lowercase t, you will get delta uppercase T equals delta lowercase t divided by n. So now we have uppercase T is equal to lowercase t over n, and we have delta uppercase T equals delta lowercase t over n. So we have got now this much information. Here we go. Okay, so next what we're going to do is we're going to write down the equation for the percentage error in the calculation or determination of the acceleration due to gravity, lowercase g. Like I keep saying, you may have heard me say this before, or maybe you did. Physics and chemistry, they care for the case. They are case sensitive. For some things, you can trade lowercase for uppercase, but for others, if you do it, it changes the entire meaning. For instance, lowercase g versus uppercase g. They're both g, but they mean two entirely different things, as you will see in a later chapter. For now, just believe me that physics and chemistry, they are in general case sensitive. So pay attention to the case. Back to the problem. G equals 4 pi squared L divided by T squared. Percentage error in G, that will be equal to delta G over G times 100 equals. Now this 4 pi squared, disregard it. Why? Because what is the error in 4 pi squared? 0. There's no error in it. We know the value of 4 pi squared exactly. I mean, sure, pi is an irrational number. It keeps going forever. But for all practical purposes, the error in 4 pi squared is 0. Next, we are going to move to this L. We get delta L over L times 100 plus 2 times delta T over T times 100. Just like you saw in the previous problem. Now I'm going to keep this in the symbolic form for now. Here's what we do. We try to solve a problem symbolically as far as we can take it. And at the end only, we should put in the numerical values. It keeps the problem neat and tidy and also reduces the likelihood of making errors and the likelihood of making the round off errors. Alright, so now what I'm going to do is, I'm going to, let me say, this delta t. I want to change its color. Let me change these colors over here. What do you want delta t to be? Let's make that blue. And let's make t to be green. Now, I absolutely do not need to make it so long, as some of you might be complaining. But I'm going to do it anyway. You can keep complaining, because I want to show this in completion. Alright, what did we say delta t was? Let's go back up a little bit, make it smaller. Delta t was delta, lowercase t divided by n. And t was what? Lowercase t divided by n. So I'm going to substitute these values of uppercase t and lowercase t into the right hand side for delta g over g times 100. Why so? Why am I making the substitution? The reason for that is I am given information about this t and this n. I am not given information about this uppercase t or this delta uppercase t. Therefore, using what I'm given, I have derived these t's uppercase. Make sense? And then I'm going to make my substitution now. Let's see. So what did we say? Delta uppercase t equals delta lowercase t divided by n times 1 divided by lowercase t. Alright, don't be mad at me here. We'll make it look pretty. T over n times 100. So from here, alright, let me quickly write this down for you guys. And then what we're going to do is, as you might know, the denominator of the denominator, which is lowercase n here in green, it becomes numerator. So here we get n over t times 100. So what happens is that, as you see, these n's, they very conveniently cancel each other out. Alright, let's go ahead and plug in some numbers here now. Delta L, what did we say delta L is? Delta L is equal to 1 millimeter and L is 100 millimeters. Alright, 1 millimeter divided by 100 millimeters times 100 plus 2 times delta t. What is our delta t? It was 1 second. Here's delta t and t is 60 seconds. Okay, let's go ahead and make that substitution. 1 and 60. We said delta t is what? 1 second and t is 60 seconds times 100. Alright, so now millimeter cancels out millimeters in the first term and 100 cancels out 100. So the first term is just equal to 1. And the second one, everybody has their own way to do arithmetic. I'll show you the way I would have done it. Alright, what I will do is, I'm going to cancel out the zeros. Then what I'll do is, this 2 here, it goes into 6 3 times. Then I have 10 divided by 3, which is 3.33. And this 3 keeps on going forever. So what do I get? 4.3%. So this is the percentage error in G. This is our part A. Alright, let's look at our answer choices here and see if any of these is equal to 4.3. And indeed, this A, G is equal to 4.3%. Next, we are going to look at delta G's value. Now, just like last time, delta G over G, okay. So we know that delta G over G times 100 is equal to 4.3. We just solved for it. We want to solve for delta G. From here, delta G equals 4.3 times G divided by 100. So now, do I approximate value of G to be 10 or do I keep it as 9.81 meters per second squared? I would look at the answer options. These answer options, 0.42 and 2.65 meters per second squared. These are widely separated from each other. Therefore, if I approximate G to be 10, I think I would have no problem. Because if I put 9.81 or 10, the answers will be just slightly different from each other. Do you agree? But these answer options, they are widely separated from each other. So we can get away with putting G as 10. Let's go ahead and put G as 10 meters per second squared. Okay, make these as squiggly lines here. So we know that it's an approximation. Divided by 100, what does this give you? This will give you 0.43. Now, if you look at the answer choices though, we have 0.42 here and 2.65. 2.65 is certainly not the answer. But even this 0.42 is not 0.43. But think about it, had we put G to be 9.81 instead of 10, our answer for delta G would have been smaller than 0.43. And what's smaller than 0.43? 0.42. So our two answers are A and C. Answers are A and C. How did you like this problem? Was it a fun problem? I mean, in the first problem, it was a straight application of the formula for propagation of error. In the second one, there was a variation. Instead of being given time period, we were given time for a certain number of oscillations. And from there, we did some logic here. We applied some logic and we solved it. And at the end, we get the same thing as we had before, right? So I think this was a cool problem. I hope you enjoyed it as much as I did. Let's move on to problem number 3 next. Problem number 3. Somewhat similar to problem number 1 and 2 and somewhat different. You will notice that in all of my lectures, based on problem solving, each successive problem is going to be built upon the previous problem. I do not want to make too many problems identical. Why? Because then it would be very redundant and boring. But you do need to practice several problems of the same kind to build confidence and expertise for yourself. In future, at some point, I do plan to make problem sets of several problems of the given kind, but for now, I'm not there yet. And this is what I have. So in my lectures, I'm going to have several problems in a given lecture, and each problem will be pretty much built upon the previous problem. So the problems will be similar, but not identical. They will be interrelated, they will be built upon each other, so you can cover a few topics, a few different concepts in the same lecture. Okay, and you can find similar problems in the textbooks. Shall we read the problem of this statement together and see what's given to us and what we're asked to solve for? Let's do that. So an experimenter uses a simple pendulum of exactly 100 centimeter length. Now here, I did warn you against the use of keywords, to look at the keywords and assume that I know what I'm asked to solve for. But some keywords are important. For example, over here, we are using this word exactly. When we're saying that the length is exactly 100 centimeters, that means we have no doubt in our mind. There's no uncertainty that the length of this pendulum is 100 centimeters. That means this implies that delta L is 0. There is no uncertainty. There's no error in the measurement of the length of the pendulum. All right. So we know that the length of the pendulum is 100 centimeters, and this pendulum is used to determine the value of the acceleration due to gravity g. Okay. The experimenter, she measures that the simple pendulum makes 30 oscillations in 60 seconds, just like problem number 2, using a stopwatch of the least count equal to 0.1 seconds. Now in the last problem, the least count was 1 second. In this problem, we have a better clock. We have a more precise clock. And the least count, the uncertainty or the error in the time measured by this stopwatch is 0.1 seconds. Which of the following statements is or are true for the observations made in this experiment? The percentage error in the time period, t. Okay, so this is the percentage error, or the error in the measurement of the time period is 1.2 seconds. All right, so we're given that length is 100 centimeters. The length is exactly known, therefore delta L is 0. Okay. There are 30 oscillations. Okay. So N, the number of oscillations, is 30. OSC dot is oscillations. In 60 seconds. Time t is 60 seconds. Using a stopwatch of least count 0.1 seconds. Delta t is 0.1 seconds. So we're asked to find the percentage error in the time period, which is delta t over t times 100. This is A. What is this equal to? And in part B, it says the delta t. What is that equal to? So we know that the formula for time period is 2 pi square root of L over G. And this experiment, though it is to measure G, in this problem though, we're not concerned about G. We are concerned only about this T and the percentage error in T, the time period. So just like we did in the previous problem, T is going to be, here's the solution, lowercase t over n. And when you differentiate this equation on both sides with respect to lowercase t, we get d uppercase t over d lowercase t equals 1 over the n. Now we are going to convert these, the differential operators, into deltas. And that will give us delta uppercase t equals 1 over n delta lowercase t. What are we interested in solving for? We're interested in solving for delta t over t times 100. So we just said delta t equals 1 over n times delta lowercase t. I'm going to divide this by what? Uppercase t, which is lowercase t divided by n. So from here, you see that these n's, they cancel out. I'm left with what? Delta lowercase t over lowercase t. The value of the lowercase t is 0.1 seconds. While this lowercase t is given to be 60 seconds. Using the rules of uncertainty, we must write the 60 seconds as 60.0 seconds. Okay. So here now we get 0.1 seconds at the top, 0.1 second divided by 60.0 seconds at the bottom. And let's not forget this 100 multiplied by 100 with each of these equations. Okay, so multiply, divide by 10 to get rid of the decimal. What does this give us? This gives us 1 divided by 600 times 100. That gives us 1 over 6. So delta t over t times 100 is equal to 1 over 6%. 1 over 6% is equal to 0.17%. So we know that 1/3 is 33.3%. And half of 1/3 is 1/6. So half of 33%, which is 0.33 in the decimal form, will be somewhere 0.16 something, right? It's approximately 0.17. So this is approximately 0.17. It is correct. If you solve it out, you will see that this becomes equal to 0.16666, which is approximately equal to 0.17. So here, percentage error in time period is 0.17%. It is correct. Now, the error delta t in the measurement of time period t is at 1.2 seconds. Now, we will solve it numerically, but before we solve it numerically, think about it. The uncertainty in time lowercase t is 0.1 right over here. And that is for measuring time equal to 60 seconds. And time period will be 60 divided by 30, 2 seconds. Could be delta t, the uncertainty in the time period. Could it be 1.2 seconds? Could it be that large? While this delta t is 0.1 seconds. Think about it. Let's calculate it numerically anyway. So delta t we said is equal to 0.1 seconds. And we also showed that delta uppercase t is equal to delta lowercase t divided by n. So delta t is 0.1 seconds divided by 30. Is this equal to 1.2 seconds? No way. This is not equal to 1.2 seconds. Do I need to even calculate this? No. Can I? Sure I can, and I'll show you how. How I would do it if I did not have a calculator. What I will do is, first thing is I'm going to get rid of this decimal. That will make it 1 divided by 300. Then I will write this as 1 over 3 times 10 to the power minus 2. Sure. 1 over 3 is 0.33 bar times 10 to the power minus 2. This gives us 0.0033. Sure, the units are seconds. We did not need to solve it. And if you don't need to solve it, and if you're taking an exam, then don't solve it. But I want to teach these classes from the point of view of learning the material, from the point of view of mastering the material and enjoying the process. The exams and the scores and the grades, they are end results. They are byproducts of learning. They should not be the end goal, even though they do turn out to be the end goals most of the times, because at the end, you're evaluated based on that. You might get admission into a college of your choice based on those results. So yes, exams are important. Your grades are important. We cannot deny the importance of those things. But if that's all we focused on, then somewhere along the process, we are going to lose the enjoyment. We are going to lose the fun in learning the stuff. And the fun lies in learning. And you really would not learn very well until you enjoy the process. Let's read the statement of problem number 4 together. In an experiment performed to determine the acceleration due to gravity. Another problem based on acceleration due to gravity. The time period, uppercase T, is found to be 0.8 seconds by measuring the time that the simple pendulum takes to make 100 oscillations using a stopwatch with the least count of 0.1 seconds. Okay, let's write down what's given to us so far. Given time period is 0.8 seconds. Number of oscillations measured, N, is 100. What else? The least count of the stopwatch, delta lowercase t, is 0.1 seconds. Okay. Then we are told the length of the pendulum is measured to be 10.0 centimeters plus minus 1%. Now this time, this is given in a different kind of format. We're going to see what it means. Let's write it down first. The length L of the pendulum is 10.0 centimeters plus minus 1%. All right. Then we are told find the value of A if the error in the measurement of G is calculated to be .5%. That means delta G, okay, here, delta G over G times 100 is given to be what? A over 2. From this, determine the value of A. That's our question. Now, we do know that delta G over G times 100. This is equal to delta L over L times 100 plus 2 times delta T over T times 100. Now, how did I get this equation? If you do not know, please watch problem number 1 that we solved in this lecture. There, we looked at how to get this equation. Now here, I need the numerical value of delta L, delta uppercase T, and uppercase T to solve for the percentage error in the acceleration due to gravity. Once I know the numerical value of acceleration due to gravity on the left-hand side, what I will do is I'll set that equal to A over 2. And from there we can solve for A. So let's see. We're told that L is equal to 10.0 centimeters plus minus 1%. From here, delta L is 1% of 10 centimeters, which is 0.01 of 10.0 centimeters. What does this give you? That gives us 0.1 centimeters. So 1% of 10 is 0.1. So this is our delta L. Cool. Now we know delta L and L. We know uppercase T, but we do not know this delta uppercase T. Can we solve for it? Sure we can. In the second problem, we solved that delta uppercase T equals delta lowercase t divided by n. So now we have everything that we need to solve this problem. Let's go ahead and do that. So delta L is 0.1 centimeters divided by L. L is 10.0 centimeters times 100. This 100 over here. Plus 2 times delta t. Now delta t is delta lowercase t over n. And then I have this uppercase T at the bottom times 100. And I know I have been advocating for keeping the equations in the symbolic form for as long as we can before we plug in the numerical values like I already did over here. I didn't have to do it, but I want to show you how to do things in different ways. In principle, ideally, I should not have put in the numbers here yet, but I did it anyway. So let's see. What happens now? Centimeter cancels out centimeter. Decimal cancels out decimal. What am I left with? 100 divided by 100 equals 1. Next, 2 times delta lowercase t. What is delta lowercase t? 0.1 seconds. Here, 2 times 0.1 seconds divided by n. What is the value of n? 100. Alright, here's our 100. Times 1 over t. What is the time period? 0.8 seconds. 0.8 seconds. Times this 100 over here. Alright, what do we get now? This is all the second term over here in parentheses. Let's go ahead and cancel out 100 with 100. Let's go ahead and cancel out seconds with seconds. And while we are canceling things, we might as well cancel decimal with the decimal, which is same as multiplying and divided by a 10. That takes care of the decimal. What are we left with? 2 divided by 8. What is 2 divided by 8? 1/4. So we get 1 for the first term and 1/4 for the second term. This is equal to 5 divided by 4. Now we're told that delta G over G times 100, it is equal to what? A over 2. So A over 2 equals 5 over 4. From here now, go ahead and multiply both sides of this equation by 2. What does this give you? This gives you A equals 5 over 2. Here's your answer. Done. So the problem probably looked a little more intimidating than it actually is. And that's how many of the problems are. They look worse than they are. They feel worse than they are. And the reason for that is we have been taught this thing. This has been put in our head that mathematics is very hard. Physics is hard. It is for some elite people who can do it. And I used to be one of those people who believed in that. I used to think that I could not do physics. I could not do math. And due to that belief, due to the self-limiting belief, I did not try very hard. I was afraid to try. I would keep on studying other subjects and totally ignore math and physics. And it was not entirely my fault. I grew up in different times than you people are growing up. And the only sources of the education for us were either books or teachers. And the books were there, but they were not as widely available and they were expensive. People like me could afford only so much. And unfortunately, for a very long time, I did not get good teachers in physics. So yeah, I was really scared of physics. But as it happened, I got some really good teachers eventually, and that helped me gain my confidence back that I can too do it. And I hope that with these videos, you too can gain this confidence. You too can learn to believe that yes, I can do it. All I have to do is put my effort into it. Believe that I can do it. And then I can do anything. Alright. Now believe that I can do problem number 5, 6, and 7 before I fall asleep for the night. Let's see if I can. I believe I can. Let's move to problem number 5 next. Problem number 5. You will see that this problem is again somewhat similar to previous problems and somewhat different. Let's read the problem statement to see what's similar and what's different from the previous problems, what we are given here, and what we are asked to solve for. The problem says the time period of a simple pendulum is given by the following expression here. In an experiment, a simple pendulum whose length is measured to be 10.0 plus minus 0.5 centimeters is used to determine the value of acceleration due to gravity, g. So let's go ahead and write down what's given to us. I'll write it over here. Then I'll copy it and move it down. So we're given this length L and delta L. So length L is 10.0 centimeters and delta L is 0.5 centimeters. Okay. Next we're told in the experiment, it is found that the pendulum takes 10 seconds to make 50 oscillations using a stopwatch of least count 0.1 seconds. Okay. So that means the time t measured is 10 seconds for how many oscillations? 50 oscillations. And the least count of this watch is 0.1 seconds. Very well. The percentage accuracy in the measurement of g in this experiment is found to be 8%. So now the terminology is slightly different from what we have seen in the previous problems. In the previous problems, you heard terms such as error in the measurement or the percentage error, but here it is saying percentage accuracy, but it means the same thing. It means percentage error. So the percentage error in the measurement of g is A%. Now remember, in the last problem, this was A over 2%. And we were asked to solve for A. Just the same way, we're asked to solve for A, rounded off to the nearest integer, is this. All right. How do we do it? Let's see. Now, we're told that delta G over G times 100, the percentage accuracy, is equal to A%. And solve for A. All right. Now we do know that delta G over G times 100 equals what? Delta L over L times 100 plus 2 times delta T over T times 100. Now all we have to do is plug in the numerical values of delta L, L, delta T, and T. Delta L's value is given, L's value is given, but delta T, where T is uppercase T, divided by uppercase T, it's not given to us. Now even though we do not know what delta uppercase T over uppercase T, these two numbers are, but we have seen in the previous problems that delta T over T, both uppercase on the left side, this ratio is equal to delta T over T, both lowercase on the right hand side. And we do know the value of delta lowercase t and lowercase t. So what we are going to do is we are going to substitute lowercase t's in the right hand side's second term. So that gives us 2 delta t over t, both lowercase, times 100. Now all we need to do is plug in numbers from this point on. So next thing we need to do is plug in numbers here. Delta L is 0.5 centimeters. And L is 10.0 centimeters times 100. 2 times delta T. Delta T is 0.1 seconds. But T over here is 10 seconds. However, the rule for the error or the uncertainty says that if the uncertainty is to 1 decimal place, then T must also be to 1 decimal place, and vice versa. So even though we are given 10 seconds here as a whole number, when I write down the value of T here, I'm going to write it as 10.0 seconds times 100. Next thing I'm going to do is, in the first term, centimeter cancels centimeter. In the second term, seconds cancel seconds. Now, we see that in the first term, we have 0.5 at the top, 10.0 at the bottom. Multiply, divide by 10. So when you multiply by 10, 10.0.5 gives you 5. And 10 times 10.0 at the bottom gives you 100. So basically what I'm saying is we're getting rid of these decimals. And I could just cancel out these decimals as long as the number at the top goes to the same number of decimal places as the number at the bottom, which in this case it has to go. Alright, with that being done, I have 5 divided by 100 times 100. That's my first term. Same way, the second term becomes 2 times 1 divided by 100 times 100. Okay, so in the first term, 100 cancels 100. In the second term, 100 cancels 100. What am I left with? 5 plus 2 equals 7. So this is the percentage accuracy or the percentage error in what? G over here. And what this is given to be equal to? A. So A is equal to what? 7%. That's your answer. Done. Problem number 6. Though this problem is also based on time period of a simple pendulum, so in that regard it is similar to the previous problem, it is going to be slightly different as well. In fact, it's going to be different enough to make you think. It's not hard, it's just different. And I think it's an interesting problem and you're going to enjoy it. Let's see what the problem says. It says that the length of the pendulum in a pendulum clock is increased by 1%. What would be the error in the time recorded by this clock per day? So now this pendulum, it is used as a clock. And the time period of a pendulum, as we have seen several times, it depends on what? The length of the pendulum. But now this length L, it has changed to L prime. So this dash, the line, which is used as a superscript for L, lowercase l, it is called as prime. And now this pendulum's length has changed by 1%. So 1% change in length. That means if initially the length was L, what is the new length now? It has gone to L prime. It is now 1.01 L. It has changed by 1%. Alright. So if it has changed by 1%, what is delta L? What is the error in the length? So delta L is going to be L prime minus L. So it is 0.01 L. So I do not have a numerical value for L, but you're going to see that we wouldn't even need it. Alright, so this is what's given to us. We are asked to find the error in the time recorded by this clock per day. Okay, so in 1 day, what's the time in 1 day? 1 day. 1 day equals what? 24 hours? Hour. 1 hour equals what? In place of hour, I write minutes. Now, 1 minute equals what? 60 seconds. So 24 times 60 times 60 seconds. It is the time in 1 day. And when you do this multiplication, you will find that this is equal to 86,400 seconds. This is the number of seconds in 1 day. Okay. Now, I want to know the error in the time recorded by this clock per day. So in 1 day, it is measuring time equal to lowercase t, which is 86,400 seconds. for measuring this much time, what is delta t? Okay. Now, I do know one thing that I have shown before, that delta uppercase T over uppercase T equals delta lowercase t over lowercase t. Correct? Alright, so I want to solve for this right hand side. Why? Because once I know this right hand side, then from here I can solve for delta t. Correct? What I'm saying is here, now we have already shown that for simple pendulum, delta t over t, where it is uppercase T, is equal to delta t over t, where it is lowercase t on the right hand side. From here, we see that delta lowercase t equals delta uppercase T over t times lowercase t. So I do know the value of lowercase t. It is 86,400 seconds. If I could figure out this relative error in the time period, then I can solve for this error in the time measured by the clock in 1 day. So let's see how we can solve for the relative error in the time period. Relative error in time period t is delta uppercase T over uppercase T. We do know that t, the time period, equals 2 pi times square root of L over G, correct? Which I can write as 2 pi divided by square root of G times square root of L, and square root of L is L to the power 1/2, correct? Now, in this case, we're going to assume that acceleration due to gravity, it is constant. We know it with absolute certainty that it is 9.81 meters per second squared on the surface of Earth. So 2 pi, this is also a constant. So 2 pi over square root of G, this is constant. And what is the uncertainty or the error in the measurement of a constant? 0. So the only variable in which I have error is L, the length of the pendulum. Based on that, when I write down the relative error in the time period t, what do I get? 1/2 coming from over here times delta L over L. Do I know the value of delta L? Sure do. 0.01 L. When L is just L. That's why I was saying we do not need to know the numerical value of the length of the pendulum. Why? Because it just cancels out. So delta t over t, both uppercase, equals what? 0.01 divided by 2. Let's keep it like this for now. Okay, then from over here, this equation over here, I'm going to use this equation now. Delta lowercase t equals delta uppercase T divided by uppercase T times lowercase t. Alright, now delta t over t, the relative error in the time period, is equal to what? 0.01 divided by 2. And this lowercase t is 84,600 seconds. Or is it 86,400 seconds? Alright, 86,400 seconds. My bad. I wrote it backwards, but I caught it too. So I'm going to get away with it. Okay, what do we get from here? 2 goes into 86,400 how many times? 4, 3, 2, 0, 0 times 0.01. So that gives us 432 seconds. This is the error in the clock in 1 day. Alright, like I said, this is not a tedious problem. It's not a hard problem. It's just different. And many times when we're doing something that is different for the first time, it takes us time to wrap our head around it. It takes us time to understand it, to get gist of it. Hopefully you got it. Good thing for you is that it's in the video format, so you can rewind it as many times as you need until you get it. If you still have hard time getting it, if you still do not understand something about this problem, like I already said, feel free to leave me a comment, and I'm going to make it a point to read all the comments and answer and reply every comment that deserves a reply. Alrighty, so this was our problem number 6. Moving on to problem number 7. The next problem, it is based on a topic that you're going to encounter in a later chapter of work, power, and energy. So you might say that maybe we're doing it a bit prematurely. Yes and no. Sure, the concepts are going to be in a later chapter, but it is still based on propagation of error. And this lecture is based on application of propagation of error to problems of what? Simple pendulum. So everything that you need to know to be able to solve the next problem, I will give you a quick overview of that. Let's get ready for the next problem. That is so far the hardest and the most tedious problem of this lecture, and perhaps most fun problem as well. Let's see it. Problem number 7, the last problem of this lecture, says that the acceleration due to gravity G sub p is measured with an error of 5% on a newly discovered planet, Zinca. I totally made it up. The energy E needed by a simple pendulum to oscillate with a time period uppercase T is being estimated on the planet Zinca. Okay, so we're trying to figure out how much energy the pendulum needs to oscillate with time period uppercase T. Let the pendulum's mass m be known exactly. That means the error in the mass is 0. Okay. And its time period is measured with an error of 3%. Alright. Calculate the percentage error in the energy. Let's write down what is given to us. Given. First thing given is here. The percentage error in the acceleration due to gravity, G sub p. Delta Gp over Gp times 100 is 5. Okay. Delta M, 0. Okay, very good. Time period. The error in time period is 3%. Delta uppercase T over uppercase T times 100 is 3%. Calculate the percentage error in the energy E, and this energy E is the energy that is required for the pendulum to oscillate with time period T, and for that time period the percentage error is 3%. And this pendulum is located on another planet, Zinca, where the percentage error in the acceleration due to gravity on that planet is known with 5%. Okay, so we want to solve for delta E over E times 100. Now when we talk about the energy of a simple pendulum that is required to make it oscillate back and forth like this, what is that energy? Let's see. Let's quickly review the transformation of energy for a simple pendulum. So here is the diagram of a pendulum, a simple pendulum. Right now, as it is shown, its location is 0. It is at its lowest height, at its lowest position, which is called as the equilibrium position. The center of mass of this mass is measured from this reference height, and the reference height is located at the equilibrium. So that means all the height is measured from here, and at this point the height equals 0. So when the mass is over here, it is sitting at what height? At a height of 0. Then what do? You're going to push it over to one side. Okay. After you have pushed it, this is going to start ascending. At this point over here, immediately after you have pushed it, it is still almost here. When it is still almost here, what is its height? Still 0. So the gravitational potential energy, GPE, gravitational potential energy, at this point is mgh. And we just said the height at this point is 0. So gravitational potential energy is 0. While the kinetic energy is going to be, well, you just gave it a push. It has started moving upward. All the energy that this mass has, that is in the form of its kinetic energy. When the mass is pushed to the right, immediately when it is pushed over to the right, its kinetic energy will be non-zero. But the gravitational potential energy, which is mgh, is going to be 0. Why? Because height is 0. This is your reference height over here. As the mass starts going up from 0 to 1, the kinetic energy is going to decrease because the mass slows down while going up, and its height is going to increase. So what happens is that the kinetic energy, it transforms into gravitational potential energy on its way up. And when it reaches the highest height at 1, it will come to rest. When it comes to rest, kinetic energy will be 0. And gravitational potential energy will be at its highest. At this point, 1. So when it is at its highest position, it will have only gravitational potential energy and no kinetic energy. But it's not going to stay there forever. It's going to change its direction and start coming downward. And when it comes back downward, its height starts to decrease. And as its height decreases on its way from 1 to 2, its gravitational potential energy will decrease. And its kinetic energy will increase because it speeds up. So when it reaches point 2, its kinetic energy will be at its highest, while the gravitational potential energy will be 0. Why? Because we said that the reference height at equilibrium is 0. Since the kinetic energy is highest at this point 2, when it's coming down from 1 to 2, it has this momentum, it has this inertia, due to which it is going to overshoot the point 2 and go over onto the other side. So the mass is going to start rising on the other side and go from 2 to 3. And as it goes from 2 to 3, it's going to slow down again. As it slows down and goes up, it's going to reach its highest position 3, at which point it will come to rest. And at that point, its kinetic energy will be 0, and all the energy will be in the form of gravitational potential energy. But again, it's not going to stay there forever. It's going to reverse its direction of motion and go from 3 toward 4. As it goes down from 3 to 4, its height will decrease. As its height decreases, gravitational potential energy decreases, but kinetic energy increases. Again, when it reaches point 4, it will have only kinetic energy and 0 potential. But due to its momentum, it's going to overshoot 4. So it's just going to keep going back and forth. At the lowest height, 0 potential, highest kinetic. So kinetic is going to push it over to one side. As it goes up, kinetic changes to potential. At the highest height, it will come to rest. It will have only potential, 0 kinetic, reverses direction, goes down. As it goes down, it speeds up. As it goes down, its kinetic energy increases, its gravitational potential decreases. It overshoots the equilibrium. At equilibrium, it has only kinetic, 0 potential. So the cycle just goes back and forth, back and forth. I hope it made sort of sense. Maybe not 100%, but that is quite alright. I wanted to give you a little preview of what's coming up ahead. Let's see what's going on in this problem next. So here's our simple pendulum at its equilibrium position. We know that when it goes up at this highest height, it has only gravitational potential energy, mgh. And this height h, it is this height over here, correct? Now what we are asked to do is solve for delta E over E times 100. And at the highest height, the energy is mgh. So if you think about it, delta E over E will be equal to what? Delta M over M plus, okay, it's cutting off a little bit. Delta GP over GP plus, we can write this as GP over here, delta H over H. We're told that delta M is equal to 0. We're given the percentage error in the gravitational potential energy. But we're not given this delta H over H times 100. What we're given instead is delta T over T times 100. So that means we need to somehow represent the percentage error in the height. Okay, multiply it all by 100 to make it percentage error. If we could somehow represent this percentage error in height by percentage error in the time period, then we have the problem solved, right? So think about this. If in this equation E equals mgh, you could somehow write h in terms of t. Then over here, instead of the percentage error in h, you will have some sort of percentage error in the time period. Now the time period of a simple pendulum we know is equal to what? T equals 2 pi square root of L divided by G. Okay. There's no h here on the right hand side. But if somehow this L, it could be written in terms of h, then I could have some sort of, h over here, maybe h squared, h cubed root, whatever. From there, I could solve for h in terms of t and put that in here. So basically, I want to write this E equals mgh, where h is written in terms of t. How do we do that? Let's see. So we know that the height of the pendulum is L. The height of the pendulum doesn't change, whether it's just, suspended vertically down or it is held at an angle theta. It's still equal to lowercase l. Now, in this diagram over here, see, I have made this right angled triangle ABC. In this triangle, hypotenuse is L, as in lion, as in London. And the adjacent to the angle theta, or the base, is L cosine theta. So you see that the height h, it can be written as L minus L cosine theta. Here, over here, you can see from this over here, that the h equals L minus L cosine theta. In other words, h equals what? L times 1 minus cosine theta. So I'm going to use this to write down the value of gravitational potential energy, E, mgh. Let's see what I get. Let's go back here. So we know that the energy of the simple pendulum at the highest height equals mgh, and we just saw that h equals what? L minus 1 cosine theta. Alright. Now, next we want to represent this L in terms of time period t. We know that time period t equals 2 pi times square root of L over G. From here, you should be able to show that L equals t squared divided by 4 pi squared times a G. Okay. Alright, so that makes E equals m times, let's write this as G sub p, because we are on planet Zinca. L is t squared over 4 pi squared times Gp, 1 minus cosine theta. Okay. We're going to do something else here. Alright. This 1 minus cosine theta. For small angles theta, this cosine theta can be expanded as 1 minus theta squared over 2 plus theta to the power 4 over divided by 4 and so on. Might be 4 factorial here. And for very small values of angle theta, this goes to 0. So the only relevant terms are going to be these two terms over here. What does this give us? M gp squared t squared over 4 pi squared theta squared over 2. Now in this equation, the only two variables for which we have an error or uncertainty are these two. M is exactly known, 4 pi is a constant, theta is a constant, 2 is a constant. So what we get for the percentage error in the energy E? Delta E over E times 100 equals 2 times delta GP over GP times 100 plus 2 times delta T over T times 100. Well, if you got this far, your problem is basically solved. So percentage error in GP is 5 and that in T is 3. Okay, 2 times 5 plus 2 times 3. That gives us 16% error. This is the percentage error in the energy to make this pendulum oscillate with a time period T, where the percentage error in the time period T is 3% and it is located on a planet Zinca, where the percentage error in the acceleration due to gravity is 5%. Yep. This was an interesting problem. I hope that you enjoyed this lecture and you learned something out of it. You had fun. With this, I'm going to end this lecture for today. I hope that you enjoyed it, you learned from it, and I'll see you again very soon in the next lecture. Until then, have a good one.